Let's look at another material shift example. 1 mole of H2 gas and 0.250 moles of S2 gas, both of them products, are placed in a 2-liter container, and we're going to assume that none of the reactant H2S is originally present. The problem asks us to determine the concentrations of everything once equilibrium has been reached. So, knowing that this is going to become a material shift problem, let's look at things just in terms of the initial moles that we've been given. We know that we've got a mole of H2 and 0.250 moles of S2 and nothing as far as the reactant is concerned. We're looking at this problem and trying to decide just what kind of problem is it going to be. And our first note is that we have a very small equilibrium constant which is favoring the reactants. Okay, so initially, since we have only products that are present, we know that this reaction is going to have to shift to the left. However, knowing that it's a very small equilibrium constant, knowing that in the end, as much reactant is going to be present as can be possible, we know that it's more than just a shift to the left, it's also a very strong shift to the left. Now, such a strong or a large shift to the left means that we will not be able to use the x is equal to 0 assumption, and that we quite likely have some nasty math ahead of us. So, unless we do something about the situation, we're going to wind up with what could be a very bad math problem, something that we maybe can't even solve using pencil and paper. Therefore, what we want to do is a material shift. The idea here is that since the equilibrium favors the reactants anyway, why not move all of the products as much as possible over to the reactant side and then approach the equilibrium problem, the ICE problem, from that point of view. So we're going to do a material shift to the left as much as possible. Now, something to be aware of in this case is that the initial amounts of hydrogen and sulfur, the 1 mole and 0.250 mole, are not in a 2-to-1 ratio as they were for problem number 2. And since they're not in a 2-to-1 ratio, one of them is going to be left over and the other one is going to be completely consumed. And so what we need to do next is an H2 limiting determination. That is, we'll use the amount of H2 that we've been given and we'll make a prediction about the amount of reactant H2S that we can produce. But we'll need to do that again for the S2 as well, because we need to determine which of the two products, H2 and S2, is limiting and going to be completely used up, and which one is in excess and is going to have some left over. We're going to begin with this prediction process with the H2. Now recall, we're going to be making a prediction about the amount of reactant. In your past lives in Principles of Chemistry 1, we never made predictions about reactants. We always made predictions about products, but the process is really just the same. So we begin with 1 mole of H2 that we've been given. And what we'd like to know is how much of the reactant H2S could we produce. So we'll need to use the mole ratio that connects the H2 to the H2S in the right order so that the moles of H2 cancel. Now this is a 2-to-2 ratio, as you can see in the with the colors. The blue 2 goes with the H2S and the red 2 goes with the H2. And as it's a 1-to-1 ratio, we predict that we should be able to, based upon the H2 anyway, convert all of the H2 into 1 mole of H2S, a 1-to-1 mole ratio. Now, we're not done. We need to make this prediction also starting with the S2. So starting with the S2, we've got 0.250 moles of S2. We multiply by the appropriate mole ratio, but in this case, the mole ratio is not a 2-to-2 as it was before, but is actually a 2-to-1 mole ratio. And the prediction tells us that we'll be able to make 0.500 moles of H2S. And so depending upon which of the two products we start with, we have 2 different predicted amounts of H2S that we can make. So what's important is that we compare these 2 amounts and make a decision as to which one is limiting and which one is excess. Now, the larger prediction is the one that we associate with an excess amount. And so we've been able to determine that the hydrogen, based upon this, is actually the excess. The smaller value, which popped up just a moment ago, is the 0.500 molar H2S. That we associate with the limiting reactant, which in this case is the S2. So we now know, based upon our predictions, that the limiting S2 will be converted completely into reactant, whereas we will not be able to use all of the H2. Okay, so we have to determine how much of the H2 is going to be left over. So this is going to require us begin with the limiting reactant that we've already determined, the 0.250 moles, and this time make a prediction about how much hydrogen gas will actually be needed to convert all of the S2 into H2S. And so this is a different mole ratio. The red two belonging with the hydrogen and the green one belonging with the sulfur. And again, what we're determining here is how much of the excess H2 is going to be required. So after doing the calculation, the math is very simple, we determined that 0.500 moles of the hydrogen gas will be consumed in this process. What we would really like to know now is how much of it is going to be left over. And again, the arithmetic is very simple, but let's go through it anyways. We started with 1 mole of H2 initially. We know that we're going to consume, as we material shift products over to the reactant side, we're going to consume 0.500 moles of H2, and this is going to give us 0.500 moles of H2 that's left over. In a nutshell, what we've determined is that as we perform this material shift, all of the S2 can be converted into H2S, but only 0.500 moles of the H2 can be converted into H2S, leaving us with 0.500 moles of H2 left over. The worst is now behind us, now that we've done the material shift, and solving the equilibrium problem is a straightforward process that, as you'll see, involves using the x is equal to 0 assumption. The arithmetic is trivial. But to continue solving this problem, we do need to tackle the ICE problem, the equilibrium problem. And to do so, we need initial concentrations. These initial concentrations are going to be based upon the mole values we calculated after the material shift takes place. Thinking back to the previous slide, we determined that based upon our calculations, 0.500 moles of H2S could be present as we had converted as much of the product into reactant as possible. Taking this value and dividing it by the 2 liters gives us a concentration of 0.250 molar H2S. Now, the hydrogen gas on the product side was determined to be the one in excess, and we also determined that there would be 0.500 moles of leftover H2 gas after the material shift took place. Dividing this by 2 liters total volume gives us a concentration of 0.250 molar. Great. Now, the S2, on the other hand, was completely consumed as part of the material shift. It was determined to be the limiting species, and thus there is nothing on the nothing left of the S2, and taking that 0 and dividing by 2, of course, gives us 0 molar. So those are our initial concentrations as we solve this ICE problem. But notice that we've got nothing on the right-hand side for the S2. And again, equilibrium requires that we have non-zero amounts in all locations. And so the fact that we have nothing, 0 molar S2, means that this is an equilibrium that will now have to shift to the right. Shifting to the right and filling in our variables means that the H2S concentration will go down by 2x. The H2 concentration will go up by 2x, and the sulfur concentration will go up by x. The equilibrium amounts, just finishing things off, will be 0.250 minus 2x for the H2S, 0.250 plus 2x for the hydrogen, and simply x for the S2. Now, the law of mass action for this problem we've seen before is what you see on screen. We'll have to square the hydrogen concentration. We've got another product, S2, divided by the H2S concentration squared in the basement of that fraction. And substituting the quantities, there you have it. Now, this at first looks like arithmetic that might be more than just a challenge. We'd have to use FOIL several times, and it would absolutely be a mess. However, in this case, we've done a material shift, knowing full well that if we can move everything over to the reactant side as much as possible, we'll be in agreement with the very small equilibrium constant that we have. And this was all done so that we would be able to simplify the math. Specifically, the 2x that we have there is added to 0.250, and this is a candidate for the x is equal to 0 assumption. But it doesn't stop there. The 2x in the denominator of this fraction is subtracted from 0.250, and it too is a candidate, and it is more than a candidate, is one that we'll be able to assume equal to 0. And the x that remains is not added or subtracted to anything, and so that will have to stay just the way it is. Now, if we make these simplifying assumptions, what we get is arithmetic that looks quite a bit simpler than what we had before. Removing the two x's from both the numerator and the denominator, and not forgetting to square the 0.250, gives us this expression where you can easily see that the 0.250 on the top cancels the 0.250 on the bottom. But nonetheless, this is something that will have to equal 1.67 times 10 to the minus 7th. The arithmetic in this case will have to solve. But we only have one value for x to solve, and as the 0.25s cancel top and bottom, we're able to very easily, with no additional work on our part, determine that the value of x in this case is equal to 1.67 times 10 to the minus 7th. To wrap up problem number 3, we need to use the value of x that we've determined after having performed a material shift and solving the equilibrium ICE problem to determine equilibrium concentrations. We also need to check our 5% to be sure our x is equal to 0 assumption is validated, and then we also need to check our equilibrium concentrations to be sure that they're correct, substituting them into the law of mass action to see if they reproduce the value of the equilibrium constant. So equilibrium concentrations, we'll start with the H2S. Knowing the value of x, we would multiply it by 2 and subtract it from 0.250. However, in this case, x is so small that within the significant figures we can report for this answer, the concentration of H2S has changed so little that we would have to write down 0.250 molar as the concentration that remains. The H2 will increase by an amount of 2x. However, again, within the significant figures we can report, its concentration is still 0.250 molar. Yes, it has increased slightly, but not enough that we can report. The sulfur concentration, on the other hand, is simply equal to x. And as it was 0 to begin with, we would report its concentration to be 1.67 times 10 to the minus 7th. Now, as we examine these concentrations, it's clear that most of the material that we shifted to the reactant side is still there. We were unable to shift any more hydrogen to the reactant side, and so its concentration is also 0.250 molar and hasn't changed much either. So only small changes to the product amounts were observed, and we have equilibrium levels, no zeros in any locations, and so one would assume that we have equilibrium concentrations to check here, and we will in just a moment. But before we do, let's have a look at the 5% rule. Remember that we had 2x that was subtracted or added to 0.250, and so this is the location that we would want to check it. We'll have to look at how 2x compares to 0.250 when we multiply it by 100 to get a percentage. And the percentage that we get is a very small percentage, 0.00001336%, very small, which of course is less than 5%, much less than 5%, and so our assumption about x is equal to 0 is validated. Very good. The last thing we want to do is check the equilibrium concentrations, and so we'll put those into the law of mass action for this problem, and that means we'll have the 0.250 squared on top, 1.67 times 10 to the minus 7th, those are the two products, divided by 0.250 molar, and without any work whatsoever, we can see that this comes back as 1.67 times 10 to the minus 7th, which is in perfect agreement with the equilibrium constant that we started with originally. So we can conclude the problem has been solved and that the answers check out.